Swayam Prabha. Digital India. Educated India.
In the previous lecture, we derived the general dispersion relation for the thin film taking van der Waals forces into account. We had achieved this by basically carrying out a linear stability analysis on the thin film equation. So we started with the general nonlinear thin film equation, we linearized it, and then we substituted the normal mode form for the disturbance, and then we got a simple algebraic expression for the growth rate in terms of the parameters of the problem and the wave number. The parameters were the Hamaker constant parameter A bar, the gravity parameter G bar, and the capillary number parameter, which is C bar. So we had also analyzed special cases where either two forces were absent or maybe one force was absent. For example, we had looked at cases where gravity and capillary number parameters were 0, and we looked at the effect of only Hamaker constant. We looked at the case where Hamaker constant parameter was 0, and then we looked at the effect of gravity and capillary number. We found that if you do not have Hamaker constant, if you do not have van der Waals forces, then gravity and capillarity would generally be stabilizing, unless the special case where we have an inverted thin film where we can have the Rayleigh-Taylor instability. And even in that case, surface tension would stabilize short waves and only the long waves become unstable. We had not generalized the general case where all the forces were present, and that's exactly what we're going to do. So we'll begin by taking a quick look at the equations and the dispersion relation that we derived in the last lecture. So the nonlinear form of the equation, the thin film equation for the height h, is given here. And if we say that at any point this h is h naught plus eta, this is a non-dimensional form of it, then we basically got a simple linearized equation for this eta, and this is the linear partial differential equation for eta as a function of x and t depending on the parameters g bar, c bar and a bar. Then we assume the normal mode form and derive the general dispersion relation, which includes all of this, and s is the growth rate. Right? We will now generalize the general case for where none of these parameters are 0. So we see that the thin film is unstable if s is greater than 0. And this essentially means if a bar is greater than g bar by 3 plus 1 by 3 c bar, right? We can substitute the expressions for a bar, g bar and c bar as 3 a bar would be a epsilon by 6 by mu u naught h naught square should be greater than epsilon rho g h naught square by mu u naught, and we also have epsilon cube gamma by mu u naught, right? We are assuming that g bar is greater than 0, which means that gravity is pointing downwards. Okay. For now, we will do it for this special case where we have a thin film that is sitting on a solid surface. Okay. So we can do a bunch of cancellations here. For example, mu u naught cancels out again. Okay, so clearly you see that viscosity disappears when looking at when determining the stability criteria. So viscosity itself will not determine the boundaries where we have instability or stability, but rather viscosity will change the growth rate. Okay, and viscosity, notice that the viscosity appears in the denominator. So in this case, viscosity would actually reduce the growth rate. As you make the fluid more viscous, then the growth rate would reduce. That's expected because it will offer more resistance to flow, and therefore the growth rate will be lower. But it itself does not basically determine the stability boundary. Okay. So let's proceed further with a few more simplifications. We have A by 2 pi h naught square has to be greater than rho g h naught square plus epsilon square gamma, right? So just like we had done in the previous lecture, we said if we define epsilon as h naught by L, which is h naught by lambda or h naught by k, all of them are the same, then we have A by 2 pi h naught square will be greater than 2 pi h0 square, and where we have epsilon, I'm going to write it in terms of h0 and k0. So we have gamma h0 square k square. Okay, so this is a criteria that we have. Now if k is large, we have short waves. If k is small, then we have long waves. Okay. So if the left hand side has to be greater than right hand side, the easiest way we can fulfill this is by basically taking the second term, which is gamma h0 square k square, to be as small as possible, and we get a necessary condition for instability is A has to be greater than 2 pi rho g h naught power 4. This is a necessary condition for stability, and this will be valid. It means that you will definitely find a wave which is larger than a certain size and which will become unstable. Okay. So we have to have a word of caution here. For a film with infinite extent, all wavelengths are possible. Right? All wavelengths are possible, and this analysis predicts. What does it predict? Analysis will predict that there is certainly a very large wavelength wave where k becomes very small, which will always become unstable as long as this condition is met. What condition is met? That A is larger than 2 pi rho g h0 square. Okay. Our analysis predicts that the thin film is always unstable. Okay. Even with the even to the stabilizing effect of surface tension. To disturbances of sufficiently large wavelength. Okay. So when we have a sufficiently large wavelength and this condition is met, then we can guarantee us we have met the necessary condition for stability. But we know that real films are not like this. There is a finite container. So for example, if I take a container here of, let's say, of width, let's say W, this is my container. And in this container, there is a thin film. So my thin film is basically exactly my initial thickness of this thin film is H0. Okay. So now I can essentially say, what is the largest wavelength that is possible? The largest wavelength possible is W goes like lambda. You cannot have a wavelength larger than the size of the container. In other words, I can essentially say W, the size of the container, will basically set the value of the smallest k, the smallest wave number k that we have. We cannot have a wave number k smaller than this value. Okay, so that's a lower cutoff that it has put. Now I can straight away substitute this in our expression. Which expression is this? So now over here, I have an expression involving A and K on the right hand side. Wherever there is K, I can substitute a K minimum. But we also recognize that K minimum is W inverse. So now using K is K minimum is W inverse. This our criteria essentially becomes A by 2 pi rho G plus gamma K square. Then gamma K square essentially becomes gamma W power minus 2. This has to be larger than H0 power 4. Okay. Or now we have instability. We can say instability occurs if H0 power 4 is less than, the thin film is thinner than a value given by A by 2 pi into gamma W power minus 2 plus rho G. Okay. Again, remember, viscosity plays no role in determining the exact value of this, of determining the criteria for the stability. Okay. And if we say, if we take viscosity into account, affects the growth rate, not the stability criteria. Okay. Let's examine this case. Let's understand what does this mean. It means that if we have a thin film which is thinner than a certain value, and what is that value? So if H is less than H critical, and this H critical is nothing but A by 2 pi gamma W power minus 2 plus rho G per half, per 1/4, then the thin film becomes unstable. Okay. So let's take an experiment, that hypothetical experiment that we could do. We would take a large petri dish and we fill it with a container with a thin film of water, and we would ask, is this thin film unstable? Right? Now, in normal laboratory conditions, there are enough disturbances to be that are present in the system to generate waves on the surface. These could be very, very tiny waves, may not be that easily visible to the naked eye, but there are still some disturbances always present in a real experiment. Now, if the thin film is larger than a certain value, meaning greater than this critical thickness, Hc, then you would expect that the van der Waals forces are not very dominant. But there are many other physical processes at work in a real laboratory experiment. For example, the thin film could constantly keep evaporating, and there will be a point where the thin film thickness becomes comparable to this Hc. And then once this happens, then van der Waals forces will eventually drive the thin film to rupture. This is exactly what happens when you just leave a thin film of water on a surface. Eventually it will evaporate, and then you basically will see tiny islands of dry spots that form. Now, you can also have what we require is that the thin film has to be thinner than a certain value. In many other applications, at the start of this discussion on thin film, stability of thin films, I had said that tear film breakup is also important. In such a problem, the drainage of the tear film itself can cause the thin film to become thinner and thinner and thinner, eventually reaching a value lower than the critical thickness Hc, and again rupture will ensue. Right? So, if the thickness of the thin film is smaller than this value, then we will have an instability, and the growth rate of that instability we've already written down again here. This is 1 by 3 G bar plus 1 by C bar. If we substitute the expressions for all of this, so we have substituting A bar, G bar and C bar. Then what do we have now? We have the expression for the growth rate. The expression for the growth rate essentially becomes S essentially becomes omega lambda, omega tilde divided by lambda naught by S essentially becomes omega tilde S essentially becomes omega tilde lambda by u naught. That's the dimensional growth rate omega. This will be equal to A epsilon by 6 by mu u naught h0 square minus 1 by 3 G becomes epsilon rho G h0 square by mu u naught plus epsilon cube gamma by mu u naught. Right? Mu u naught mu naught cancels out. There is no mean flow. The characteristic velocity will naturally disappear, and therefore what we have now is we have 3 mu omega tilde will essentially become A k square by 2 pi h naught minus h0 square k square rho G h0 square, and finally I have the surface tension term, which is f0 cube k power 4 times gamma. Right? So we recognize that then the dimensional wave number k tilde would be k h naught, and therefore wherever there's k, I can simply substitute k tilde by h naught, and therefore we have 3 mu omega tilde essentially becomes a k tilde square by 2 pi h0 cube minus k tilde square rho g h0 plus 1 by h0 k tilde power 4 times gamma. And the growth rate essentially, the dimensional growth rate essentially becomes 3 mu omega tilde becomes a by 2 pi k tilde square by h0 cube minus k tilde square by h0 times rho g h0 square plus gamma. So this is the dispersion relation in the full dispersion relation in the dimensional form. What is this? This is the full dispersion relation relating the dimensional growth rate omega tilde to dimensional wave number k tilde for various values of A, the Hamaker constant A, gravity G, density rho, surface tension gamma, and finally the thickness of the thin film H naught. Okay. We can use this expression and of course the viscosity mu. We can actually use this expression to make plots of omega tilde versus k tilde, right? You can clearly see that when k is 0, which means that it's a perfectly flat interface, then you will have no instability, okay? And this is consistent with what we have seen earlier, that you have to have the van der Waals has to exceed a certain value, so you would have some kind of a growth like this, and eventually this growth will cancel out at some large value okay. Beyond a certain k, surface tension would stabilize. So we finally derived the general dispersion relation in terms of all these parameters. We can use realistic values of all these parameters for a general thin film and find out what is the typical growth rate. How long does it take for the thin film to rupture? We've derived the general form of the dispersion relation for the dimensional growth rate omega tilde in terms of the wave number k tilde and all the other parameters that are present in the problem. We have now derived the general dispersion relation for the dimensional growth rate omega tilde in terms of all the dimensional parameters in the problem. That is the thickness of the thin film H naught, the wave number k tilde, gravity G, density rho, surface tension gamma, and viscosity mu. This concludes the discussion on rupture of thin films. In the next lecture, we'll be looking at another very important instability problem termed the Marangoni instability, which is again an instability that occurs because of surface tension, but more importantly, it occurs because of variations in the surface tension at an interface. Thank you.